Hello guys, let me check if my stream has started. Started. So today we will be studying Recursion part 2. In the part 1 video we tried learning about what? Yeah, so we did binary exponentiation, and using that we were able to find the power. Let's revisit this problem. So in this, if n was negative, this was for the constraints. So yes, we are doing the half of the power. We are dividing the power by 2 and then squaring the result of it. Is that what we did? Yeah. So we took the example of 2 raised to 7. So as 7 is odd, that is n divided by 2 is odd. So we'll do 2 raised to 3. 2 raised to 3 is 8. So we'll multiply 2 raised to 2 raised to 3 into 2 raised to 3 into 2. So that will be 2 raised to 7. This way we reduce the time complexity. So this was matrix exponentiation, not matrix, binary exponentiation. Then counting good numbers. Counting good numbers. So a good number was on the odd positions, it has prime number, whereas on the even positions, okay, this is even position, it has even numbers, and odd position it has prime numbers. So we use PNC concepts wherein we'll have 5 ways of putting numbers here, 4 ways of putting numbers here. So we have, so how many even places and odd places we have, that we have found here. Now that's here. This is the total even places. This is the total odd places. Okay. And yeah, so we are trying to find something raised to something. So now in order to find 5 multiplied by itself this number of times, so whatever this second thing is, we'll divide it by 2. So this is my power function. So whatever my second part is, I'll divide it by 2. Whatever I get the answer. Okay, and if that second part was even, then we straight away return half multiplied by half. If it was odd, then I'll multiply half multiplied by half multiplied by 1x, and this mod is to cover it up. And yeah, this was about count numbers. Now sorting a stack using recursion. Given a stack, the task is to sort such that the top of the stack has greatest element. One second. Given a stack, the task is to sort such that the top of the stack has greatest element. So what we did was, using recursion, we took out each one of the element till there is nothing. Okay, so that is done using a recursive sorted function in which the stack is passed, and we do it till the stack is not empty. And till then what we do is top is equal to stack.pop, we remove the top and sort, and again call the same function. So in the last iteration there will be nothing. After that, when the stack is empty, this function will be called add greater at the top. So whenever there is nothing in stack, if not stack, then we straight away append the top, which is the other condition when we'll append the top. So we want the output as 1 2 3. So if my previous element was 1, my next element will be 2. So if my previous element is smaller than the current element, so if previous element it is smaller than the current element, then I'll append it at the top. What if it's not following that condition? Then whatever is at the top, which is s is -1, so this thing is greater than this, so I'll just remove that. Current is equal to s.pop, and then I'll call this function again, adding greater at top. So we'll put it there, and then we'll put back our current element. So this was about sorting a stack using recursion. Something to remember: sorting a stack using recursion. Reverse a stack using recursion. What did we do here? So here we are straight away reversing a stack. So it is same. First we'll empty the stack. So this is the condition for exit condition for emptying this reverse. We'll keep on removing. Once everything is removed, I'll call insert function. So if there is nothing in stack, I'll straight away insert this element and return. Wait a second. 6934. In case of the command of putting 1 at the start. I check the editorial ones. Why did I write this? Exterior pen item. Coding with an extra space. Recursive function to reverse the stack. I don't understand why I wrote this in this solution too. Oh, this was only for if not stack. Otherwise what we will do is we will pop the item, we'll pop the atom and we'll call insert function again, bit top. So what is this? Time complexity is n square, since we need to call function. So this one is let's look at there. Function is at the bottom of the stack. Insert at bottom. This is the define function. Okay, so reverse, they are calling reverse. So dot function stack. If it is greater than 0, then we are popping dot function reverse. Again calling the function reverse, and then inserting at bottom. And then insert at bottom, what they are doing, checking if there is nothing, then we'll just put in the atom. Otherwise, popping the element out if there are, say, 1 2, so popping 2 out, self insert at bottom, again popping 1 out, and then I'll append 1 in stack 1 2. Okay, so in this way we are reversing a stack. So this will take off n square complexity, since we need to call the function, this function. Okay, recursively call insert at bottom, which can again call itself a recursion, hence of n square, and we need no extra space, hence of 1. Now if we want to optimize this, of course we have the trade-off. So they are taking a queue in order to reverse a stack. Nice. So what they did was they took a queue where stack is not empty, pushing everything into the queue, and while queue is not empty, pushing everything in the stack. Okay, so this was the stronghold that we got. Let's see, based on that hole, what we are able to solve, and we'll look at the problems, how to solve them. Subsequent patterns: generate all binary strings, generate parentheses, print all subsequences, learn all patterns, count all subsequences, combination sum, 1 2, subset sum, and then we have n queens and all, rat in a maze, word break, m coloring, expressions. Okay, so I guess these are the standard problems. Let's start with generating all binary strings. Generate all binary strings without consecutive ones. So case 3, so for length 3, we don't want everything with consecutive ones. 0 0 1 0 0 0 1 at different places, and case equal to 4 1, so 1 at different places, then 1 at alternate places, 1 at last place. I mean that if string ends with 1, then we can put 0 only. String ends with 1, then we can only put 0 at the end. String ends with 0, then we can put both 0 and 1 at the end. Below is the algorithm. So let's think. We generate all substrings starting with 0. If n is equal to 1, generate all strings, k strings. If n is equal to k, print string. Previous character is 1. String, put string n is equal to 0. Generate all strings. If previous character is 0, we firstly put 0 at the end and call the function put in string 0, generate all strings. Put string of n is equal to 1. Okay. Bruh. Let's see what they have given. 2 raised to n. What is the time complexity of this problem? This thing? 2 raised to n. And for this it's 2 raised to n space n. This is space k. Space n. And then another easy recursion method to generate one. So this is another 2 raised to n, and space is also 2 raised to n. Alright. Generate all binary strings. Let's go through this once. So generate all strings. Qtel. What is k? The length of 0 1 0 or whatever it is. What is string? What is n? Print binary string without consecutive ones. So if n is the current size, I guess. If n is equal to k, terminate binary string and print string till n separated by nothing and ending with this. Yeah. So this is the exit condition for our binary group, and for a recursive function, and if previous character is 1, then we put only 0 at the end of the string. Example str01, then the new string will be 0 0 0. What? If string n minus 1 is equal to 1, then string n will be 0. Generate all strings until k string n plus 1. If previous character is 0, then we put both 1s and 0 at the end of the string. Okay. Shouldn't it be 0 1 0 here? If it's 0 1, then we'll put 0 0 1 0, right? I don't know. If previous character is 0, then if it is 0 0, then it can be 0 0 0 or 0 0 1. Yeah, understood this, but this is a bit sketchy for me. If strn is equal to 0, then strn is equal to 0, generate all strings, okay, n minus 1, okay. And then for generate all strings, base case. If k is less than or equal to 0, then nothing. 1 by 1 stores every binary string in length k. This for storing the answer, and generate all binary strings starting with 0, and then generate a binary string starting with 1. And what am I doing here? Oh, here we are printing it, not taking any other data structure. So let's see if there is any similar question on LeetCode. Generate binary strings without adjacent zeros. Yeah, this is the same question, I guess. Generate binary strings with adjacent zeros, without adjacent zeros. So if first one is 0, there won't be 0 again. Yeah, so let's start with the logic for this. So we know that we have to slowly build a string of length n. So, and how are we supposed to return? We're supposed to return in a list. And yes, we are supposed to the answer is a string, right? Okay, so let's answer is equal to this. Then I will call two functions. Let's call a recursive function first. So there will be a recursive function. We'll try to give some better name. Generate valid strings. So generate valid strings. We keep on generating valid strings. It will take the length n that we know. What else should it take? The current length, and what and the answer. Okay, so first thing first, so in order to generate valid strings, okay, so if what is the length of n? N is between 1, so if n is equal to 1, I'll straight away return 0, 1. Yeah. And otherwise I'll start my if it is greater than 1, then if it is greater than 1, then anyways once I'll start from 0 and once I'll start from 1. So while starting from 1, how will I call this function? Control C. Generate valid strings and do self dot generate valid strings, and will be passed automatically, that is 2 at this time. Current length will be 1, and my answer will be as it is. This is it, right? Wait a minute. So this will generate me, but what is the starting string? Do I need to have the starting string also? Current length is 1 and it will be 2, and answer will be here, but this function needs the previous size also, right? What previous thing is there? So let's say this is the string, current string. My current string will be what? Current string will be 0. Starting with 0 and then starting with 1. Then after doing all this, I'll return answer. This looks good. Now defining this main recursive function that we have, generating valid strings. In order to generate valid strings, what do we have? If current string, so current length will always be lesser than n, right? If current length is equal to n. At that time I'll add it to the answer. Otherwise, what I'll do, I'll look at the previous. If current strings last element is equal to what? If it is 0, so the question says that without adjacent zeros. So if it is 0, then I can only have 1, else I can have 0 and 1, right? So I can only have 1. That's why I'll call the generate valid strings n. In this, my current string will be current string plus what? 1, and n will be same. Current length will be increased, plus 1. Answer will be carry forwarded. Similarly, here I can have two. We can have either 0 or 1, and similarly for everything. Now for this, if current length is equal to n, what happens? If current length is n, what does it mean? It means that whatever is my current string, I have to add it to answer. Yeah, so we answer dot append oh my god, current string. We've written something. Int object is not scriptable. Wait, why is my current string an int? What am I passing to current string? Current string is Jama. This is my current string, this was my n. Wait, where did I start everything from? Generate valid strings with 1, starting with 1 and starting with 0. Memory limit exceeded. What do you mean? Am I sure that I'm increasing current length? Always. This current length is n is string same, but let's start from here. Suppose n is 3. So answer is 1. If n is 1, then my answer is this. Otherwise, if n is greater than 1, n is not 0, right? If n is greater than 1, then I'm generating valid strings starting with 0 and starting with 1. N is same, and current length is 1 because it has this. Answer is same, and then I'm returning answer. So answer is something that is getting carry forwarded and increased. Then this answer is passed here. Okay, so if current length is n, no, n is 3, whereas current length was just 1. If 1 is n, it doesn't go in this loop, doesn't append anything. Okay. If current string its last element was 0, then I can only have 1 in front of it. So I'm generating all the valid strings. Whatever the current string was, I'm adding one to it. String concatenation. Current length will be increased by 1 and answer will be increased by, answer will be same, else it will have 1 in the end, right? So generate valid substrings or add either 0 or 1 and current length plus 1. Yeah, so it goes on calling, and at a point this current length thing becomes equal to n, right? And it will answer the append string and return. Is it because of this return statement? Oh, so this exit condition wasn't actually exiting. So here we go, we were able to solve one question. So we are getting a stronghold on recursion right now. Go into solutions, backtrack as it is, please abort. So what have they done? Let's go directly to the solution. Valid strings, result, self-generate strings, result. This is the answer of all them, and n and -1. Generate strings, if length is n, then append dot join return. Add one to string and generating this. Okay, and then they're popping it. Add 0 to the string only if the last character was not 0. If last character is not 0, SB dot append 0 generate strings. Okay, this is another way. Are you Google? Nice question. Just because his name was Saket. Helper function for int is int for last character. So if you answer string, while you generate, you will use either 0 or 1. Initialize you can give as the recursion will start taking. So you put last character as 0 when you answer, and the rest code will work for the money. Well, what has he done? Let's aim to generate binary strings too. So this is what he has done. Has a mutable list SB to build the string. Tracks the last character added using last character to decide whether 0 can be added. Uses append and pop to avoid string copying. Better space efficiency. So self-generate valid strings. Yeah, this was my approach. Start considering both possible first characters and use the immutable string build strings using plus yes, which creates a new string every time, more memory intensive. Okay, so his is better. Checks current string -1 to determine if 0 can be added. Approach one validation is if last character is not 0, then in string builder he is appending 0. Logic is decoupled from the actual string content. Logic is decoupled from the actual string content. Plus 2 if last current string -1 is 0, uses direct explain last character build. Simpler but can be less efficient due to string copying and slicing. Uses list append and pop for efficient, and string concatenation is less efficient. Okay. More optimal, reuses the same list, creates new strings. Slightly more complex, simpler to read, may need more string operations, easier to we build string characters by character recursively, making sure we don't play 0. So last character this. This is not his. Come on, man, I didn't ask for this. So base case is if length of SP is n, then result dot append. Dot join result dot append. SP dot join SP. Return. Joins the character list SP into a string and adds to a result. Wait a minute. Always try adding 1. String builder dot append 1. Self generate strings SP and 1. What is 1? This is the last character, I guess. Saying the last character was 1, I'll generate all these strings and then I'll remove 1 and add 0 only if last character was not 0. If last character not 0, SP dot append 0, and then tell them that last character was 0 and then remove it again. SP dot pop. So last character is nothing, so it will go to both of them. Yeah, let's go back, adding 1 to the string, SP dot append 1, and then self dot generate string, and then I'm removing it from the same, and then again checking if last character is not 0, then I'm adding 0. Okay, so adding, popping and adding in the same function run. Perform its different function runs for 1 and 0. Got it. This one is done. Generate parenthesis. Generate parenthesis. Given n pair of parentheses, write a function to generate all combination of well-formed parentheses. Input 3. What will be 3 starting, 3 ending, 2 starting, 1 ending, 2 starting, 1 ending. How do I generate given n pairs? So 3 pairs, so length will be 6. Now how do I find this output for observing one thing here, that I start this, start, 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 end. How do I do this? So if I use the same string builder logic, then every time I have to start with the opening bracket, that we know. What can be next? So while working with parentheses, every time I've used this thing called balance. Okay, so I'll start with open always. When I start with open, and my balance will be balance is equal to +1, because there is one bracket that is not satisfied yet. What will be my exit condition? Exit condition will be if length of my string builder is equal to n and my balance is equal to 0, then I will do answer.append string builder. This is my exit condition that I found. About all things, so we are building it from the start, and for that we are using recursion just like the previous problem. So I'll start my string with this. This will be my initial string. So what are the attributes? What are the parameters in my function? So let's say my function is help generate. Okay, what will it have? First of all, help generate will have a string builder, that is the current string. Okay, string builder is done. After that we'll have n for sure. We don't need current length, we could have calculated using length of SB anyway, so let's use as less parameters as possible. SB and what else? Balance, and main thing is answer. So yes, this is how we get. I think I can generate logic based on this. So first of all, let's make this as a different function. Okay, this is my function. Now how will I start? Looking at the constraints, it can be equal to 1. So if we know that if n is equal to 1, if n is odd, then no, it's not what I think it is. Dumb. Wait a minute, it's not the length, it's the number of brackets, right? So if length of string builder is equal to n, if length of string builder is 2 times n, okay, if so, and if even if n is 1, the logic will work, so there is no edge cases here. So I'll straight away start the logic. I'll take an answer as an empty bracket, and I'll straight away pass it to help generate. Self.help generate, and then we'll take all these things. So string builder will be opening bracket always. N is n, balance is 0 as of now. No, balance is 1 because here 1 is there, and answer is this. Okay, Or should I take a variable answer and then return it? Or should I return this? No. Wait a minute. What happened in the previous problem? How did that guy return his answer? So he had result. Valid string. Oh, he took the result separately. My bad, my bad. Answer is equal to empty brackets. And then I'll return answer. Yeah, so this is done. Now the main logic here. So let's copy paste our exit condition. If length of SB is string builder is 2 times n and balance is 0, then answer dot append this. So this is done. Now if now the main problem is every time I go negative, that is if I'm starting with the open bracket, close bracket, so it is 0, and if I do this and if it is negative, then this won't go forward as a right string either way. So whenever it goes negative, I have to cancel that recursion. So let's use the cancelling recursion. How? If balance is equal to balance is less than 0, balance is there, I'll just return. Okay, I'll straight away cancel the recursion. Now the other condition is balance is not equal to 0, balance is not less than 0, so balance is greater than 0. So if balance is greater than 0, what can I do? I can either add a closing bracket or an opening bracket. So I'll help generate another subsequence, help generate, so help generate string builder. So now I can either add opening bracket, balance will be adding this, balance will increase, balance plus 1. Oh wait, there can be balance is equal to 0. If balance is 0, then I can only add it. And if balance is equal to 0, then just add it, nothing else. And then else we have two options. That is, I can increase one open bracket, then what I'll do is after increasing it will do something to my string builder, right? Wait a minute, why did he use pop function then? Go back to the previous question and see how he did it. So he is appending string builder to this one and then generating strings and then popping. Okay, so instead of directly appending, if balance is 0 or let's do the same. String builder. Oh, is string concatenation a heavy process than appending to a list? Why am I asking Google? Can ask lead code. Is string concatenation heavier than list append? String concatenation inside loops or recursion is generally heavier than append or dot join for several reasons. Immutability of string. Python immutable. When you do something like this, Python creates a new string each time, allocating new memory, copying contents. Append is in place, lists are mutable. So okay. So what I'll do here, one subtle change is, when we are starting our thing, we'll start with this. Okay, so now it is a list of characters, and every time we go in, what we'll do is, whatever the string builder is, I'll append as an element. The only change here, it will be, instead of answer.append as b, answer.append empty string dot join. Is it right? Dot join as b. Yeah. So we made a little change here, adding and then popping. So similarly we'll do it here, and I'll pop. So we'll do a pop, and then again string builder dot append. I'll just pass string builder here, and then I'll do string builder dot pop. Oh, I can do both of them, right? Is this good? This is the only time I'm using a closing bracket, so my balance will go down by 1. Alright, so I think I'm good, but I don't know, am I forgetting something? Maximum recursion depth. Yeah, so after getting answer, always return maximum recursion depth. Help generate. I'm appending this and increasing the balance. Okay, if length of string builder will be, wait, what is length of string builder? String builder dot append. So this was string builder with length 1. What is this? Balance is 1. Then if balance is less than 0, I don't care about it, about that recursion. If balance is 0, then I can only add opening bracket and increase the balance. SB dot append this, length of SB is increasing. It is checking if length of SB is equal to 2n. 2 3 the 6, and balance is 0, then only I'm adding. If Oh, wait. What if balance length of SB is equal to 2? Okay, so length of SB is equal to 2n. Then anyways we are on the verge to either return or do something. Then if balance is 0, then only I'll append it, otherwise I'll return it. This is the change that is needed. Okay, so one answer is correct, one answer is wrong. Terrible. So my output was 1, 2, 3. So what was the length here? 3. And then when my balance is greater than 0, I'm appending opening bracket to the SB, increasing the balance by 1. So this one came into picture, and wait a minute, why is my length just 1? I'm calling help generate, right? Did I add it to answer? Yes. Answer dot append something dot join string builder, whatever my string was built till now. If my length, so this is for if balance is less than 0, and if balance is equal to 0. What are the case? Other cases, balance is greater than 0. What if I put this first? Do you have to write this also? I don't think so. Oh, okay. Submit this. Let's go. But it isn't as fast as they want. So now you're using recursion balance counter to generate all valid combination of n pairs to balance a classic and elegant problem. Let's break it down. Clearly what code is doing. For a minor improvements you might consider generate all string n pairs so that the balance each this must have this. At no point should closing bracket exceed opening bracket. Yeah, this key idea is use balance variable. Yeah, 1 minus 1. This is what I used. Only is valid balance is 0. One string reduction to n. The recursion prunes path where balance. Yeah, recursion pruning path invalid. Function walkthrough. Help generate this as current list of characters. Balance base case 2n. The current string length. The current string length 2n is valid at the if more balance is equal to 0, then I'm appending this as beta append this, generate whatever is there, and then I'll pop it. The only valid move is to add, otherwise balance would be negative. If balance is greater than 0, then I can add both of them. At this point you can either add to a new group or close the existing group. Entry point, this is entry point. Why placing 1 and then setting balance? Sampling and minor cleanup suggestion. You can simplify the conditional logic inside help generate. So what they have done here, removes the redundant f to make the logic a little greater. Yeah, so balance is less than 0, return. Balance less than 0, return. Balance is equal to 0. Always allowed to add. Yeah, okay. So anyways it is always allowed to add this. So why do I even need to write this? It's still the same. Let's see what people have done here. General parenthesis and result current backtrack open close. If open is equal to close is equal to n, then only we add to the result. Okay. and backtrack will only take open and close. If open is less than n, then current dot have and opening string. So there will be exactly equal number of open and close, and open will be n and close will be n. So if open is less than n, then I'm adding this, and backtrack open parenthesis plus and closed, and current dot pop, and then close parenthesis less than open this. Wait a minute, how does this work? First I'm giving that I have 0 close, 0 open. This is the entry point of the program. Then it goes to this function, and first it what it does is this is the exit condition, and if open is less than n, then I'm appending this. Current, okay. So this goes as a one leaf of tree, this goes another leaf of tree, recursion tree, and then they keep on building themselves, and on the final leaves they'll add themselves. Oh, this is a straightforward approach. Good. How much time do we have? I think this is it. There are many problems left in this. We are only able to do this 2 problems. But yeah, it was a good practice. In these problems, we were trying to build something using string builder. So we are like going from the, what was the nature of the problem here? So we start with a base thing that we have, and then we find our ways. Okay, and sometimes when some of the nodes they get pruned, whereas some go forward and they find their answers, and here the condition check is done, and some go out, and all these things come. So this is one part of recursion where we build our recursion tree downwards, and we don't need to go back. The answer lies at leaves. Okay, so this is one thing that I'll remember from these 2 problems. So that's it for today, guys. Thank you for studying with me. I don't think we are cracking Google with these 2 problems. We need a lot of practice. Recursion itself will take like how much hours? 5 hours more just to solve the subsequence pattern if I go at this speed. But let's see how far we go. Some of the problems here I've already solved them last summer, so it's like almost a year ago. So I have no idea if I remember even a single thing. I don't even remember what n-Quin's problem is. So all we need is practice. Thank you for watching, guys. See you in the next stream. I don't know about what it will be, but let's see.